Welcome, Mechanics of Materials students. For this short lecture, we're going to take a look at what I like to call the tale of three cylinders. And this is drawn from problems 1.77, 1.78, and 1.79 of the Vabel Mechanics of Materials. Madkar Vabel from Michigan Tech. It's an open source Mechanics of Materials textbook. So for these problems, we've got two semi-concentric cylinders. They're concentric but only partially overlapping. So we got one cylinder, and it has an outer radius, or excuse me, an outer diameter, a diameter of 70 millimeters, and we'll just put that right into meters. E to the minus 3 meters. So we can say it has a radius of 35 times e to the minus 3 meters. And it's being joined to another cylinder, which is smaller, by exactly the wall thickness of the first one. So this other cylinder, the smaller one, has same wall thickness. And it has a diameter of 50 millimeters, or a radius of 25 times 10 to the minus 3 meters. So wall thickness in both cases is 10 millimeters, or 10 to the minus 3 meters. And we're given a couple of cases. This is actually a cylinder in here. Try to draw that a little more realistically. Pardon my isometrics. So we have three different loading cases that we can consider. And the three problems step through them. So we're just going to kind of look at them all together. Because they give us a good review of shear stress on a cylinder in three different orthogonal directions. And we're going to draw a little cylindrical coordinates grid over here just to reference, or our coordinates in fuchsia. Let's orient it the same way we're doing the cylinder. So we've got the z-axis, we'll call it going straight down the cylinder axes, and then we've got an r coordinate, which is going to be leading to kind of like the face towards the outer circumference, and then we've got theta, and let's draw it so our right hand rule is correct, which goes along the cylinder, and of course these are orthogonal, all of them to each other. So we have an r theta z. So something that is like this, if we were to grab this cylinder and pull it with a force P, maybe we would be applying that force to the z face, and it would be in the z direction. So it would give us a normal force zz. If we were to apply torques, we could apply them in multiple different directions, and in fact this normal force being applied to the end of this cylinder here, when we look at this interfacial area, maybe the two are inserted a little bit more into one another, but we're going to pay a lot of attention to this interfacial area. And in fact, let's break it out and let's kind of show it as a hoop here. Right, so this is the surface on which these concentric cylinders are touching. So this is all 2D. So here's our Z and our R, and then theta would go down kind of in the circumferential direction. So we can, I'm just going to go ahead and draw the other loading cases. So loading case number 1, keep the same color here, is, let's Draw it over here, keep this in static equilibrium. This face. So we can apply normal force P applied in the Z direction to the Z faces. We could also apply a torque, T. Our Vabel book likes to call it T. And of course, to keep the whole thing from spinning in the air, we're not going to apply any rotational acceleration. This isn't dynamics. So we're going to apply another torque over here to keep it in static equilibrium. But we can call this, actually we only have 2 loading cases, but one of those loading cases, two loading cases, torque applied to the ends. And let's figure out how we're applying that torque. We would end up showing the moment vector like that. But let's give a thought about, you know, which direction we're going to end up producing a shear force in. So we can say basically the torque vector, we'll just call it in the Z direction. Okay, so let's get back to our shell, our 1D surface, our cylindrical surface, which is this one here, where these two cylinders are touching, where they're inset to one another. If we look at our force P yanking, we're going to end up producing a tau, and let's get another color here to show our shears, our shear stresses. We're going to end up with a tau that is in the Z direction, but applied to the face that would have a surface normal in the R direction. So this is going to give us a tau RZ. P gives tau RZ. So it's going to kind of be, you know, be pulling back and forth this way. So it's going to be acting over this whole surface, but in the Z direction. Now, if we twist, we're also operating on that Z face, in that if we took a surface normal to this ring-shaped surface all the way around here, it's definitely the Z face. You know, we got our little cylinder here. Here's, excuse me, R face. I apologize. R face. Z face is out here on the end. R face. So here's our unit vector R. So anything on this curved surface is going to have a surface normal in the R direction, radial. Radial to curved surface. Apologies for that. So tau, our shear, is acting on the radial surface, and in the case of yanking, we're operating in, that shear is going to operate in the Z direction. But if we twist, we're going to end up getting shear in the theta direction. So tau, or the torque, is going to give a tau on the R face in the theta direction. So when we take a look at adding up the area over which these shears are operating, we're going to add up different areas, and we could give it a differential area. We could add up the area of this hoop by doing an R theta, or we could just do it algebraically if we know something about the overlap that we're, you know, where we're going to be operating. So we're going to start out by just thinking and orienting ourselves of which direction force results in which shear on what face and in what direction. And because shear stresses are very frequently applied to cylinders, torsional shafts being the big one that we'll get to specifically later on, I wanted to take this as an opportunity with these questions to kind of reframe them in our r, theta, z directions a little bit as we go through the problems. Okay, I'm gonna move around a little bit and give a little bit more room here to work some problems. Okay. So I'll grab another color here. So zeroing in on our first problem, so we're going to go case 1, and I may have to replicate a little bit of the drawing. So we've got the cylinders, and I'm just going to draw them in cross section. I'm going to do a, like it's called a section view. Here. So if you're familiar with CAD, I split these right down the middle. So I'll do a little cross hatching. So this is the cross section, the longitudinal cross section where these are joined. So we're told that the pipes, we've got an adhesive in the middle here. We'll draw that with another color. We're having a good time with colors. So you've bonded them with an adhesive here. And that adhesive exists over a length of 200 millimeters. So that's 200 times 10 to the minus 3 meters. And we've got the same outer diameter. We'll say we have that radius of 25 times 10 to the minus 3 meters. So now we've effectively defined, and I'm going to break it out into the orange. Now we have this, if we assume that the adhesive thickness is negligible, which most bond lines are pretty thin. So we'll assume that we have like a negligible bond line thickness here of the adhesive. We can define a surface area of just the adhesive if we took it out over here. So we could say the surface area equals pi times 25 times 10 to the minus 3 meters squared times 200 times 10 to the minus 3 meters. So that would give us the area over which our shear stress can act. So we could then define a V pulling back in this direction. We'll call it V adhesive, because tau is acting on the R face but in the Z direction. So it can oppose that applied force that was in the Z direction. So hey, stresses have to be lined up in the same direction of forces to oppose them or augment them. So we're kind of we're going in the right way. So if we integrated over that area, or just multiplied area by the shear stress itself, given that we're going to assume that the shear stress is uniform, we can say it's just the shear force, which is going to be in the Z direction, is shear stress times the surface area. So we're told the two pipes, so we're given a failure stress. So maybe this was a test. So somebody maybe put this together and pulled it apart and on a universal test machine, like Instron test machine type of thing, and said, okay, at P equals 100 kilonewtons, so 10 times 10 to the third newtons of force, what was the average shear stress? Well, hey, P in this case is lined up in the Z direction. It's being opposed by nothing more than V adhesive, so we can say P equals V adhesive everything in the Z direction, right? So we kind of did an equilibrium in the z direction, and we just said that's equal to tau times the surface area. So we can say tau equals 10 e to the third. Oops, I gotta make a correction here. That was a volume. Oops. Surface area of a cylinder, 2 pi times r. I was finding this in a follow-on units check, so whoever caught that ahead of time, and congrats. So we have tau is equal to our applied force divided by our surface area, which better have area units, so 2 pi r, 25 times 10 to the minus third meters, times, which is our radius, times our length along for the adhesive bond, times 10 to the minus third meters. So we have newtons per meter squared, so this should give us a value in pascals. So I won't go through the calculator punch, but you can do that if you're interested, and check it if Fabel has an answer. But that's the approach for our case 1. So let's move on up and take a look at another case. So now we're going to draw from problem 178, which is the twisting. So we've got our I'm going to draw that same longitudinal section. Oh, and my tablet decided to give me a straight line there. So we got the same situation. We got, one pipe nested inside another. And I believe we got the same dimensions. And these are kind of not drawn as well to scale. They're showing it being a little, I'm showing it being a little too different. Oop. Let's try that again. Apologies. And I'm going to hold to maybe a blue for the pipe and an orange for the adhesive. We'll be a little more consistent here. Anyway, we were going in the RZ direction with our shear. And this time we're going to go in the R theta direction. And that's going to give us a torque. We're going to apply that over the surface. Now, you're thinking probably, hey, wait a minute, shear, torque. We got an extra R involved in there. I'm drawing that a little bit too thick. Something important to remember about these pipes, this is all at the same radius, and that's the important thing. Our adhesive, because it's a thin layer in this case, we can assume that our radius over which our shear force, which is going to be going in the R theta direction, so it's going to be kind of, we can think of our shear force kind of on the section we're looking at as going like that. So it's on the R surface, and it's going at the theta direction. So on this section, it's like it's coming straight out of the board and into the board at us at every point along here. Now, if we were going to reference that to the center line of the cylinders here, right? Because that adhesive layer is thin, it's all at the same R, the same radius. So we can correlate whatever the shear stress is, or the shear force due to the shear stress, and we can just set it all at a single radius. We don't have to integrate a little bit of force due to a bit of shear stress, over a range of radii, because we've got the same R applying to the entire thickness of the adhesive bond. It isn't very thick radially. It's got a very small dr there, so we're going to assume it's all the same. So we're making another one of those small angle assumptions. Okay, so we can come along here and say, okay, our torque external is going to have to be, basically we'll call it our torque internal from the adhesive. Adhesive is going to be what gives it to us. So we'll call it our torque T adhesive. The magnitude of it is going to be equal to R times our shear adhesive. And we're just going to remind ourselves that's going to be on the R face in the theta direction. And that's, of course, the shear stress times the surface area. And we may have a different shear stress, but we have the same surface area that we had before, assuming we have the same bond length and the same R here. So the surface area is going to just be 2 pi big R, and I'm just going to write this in terms of some variables here. I'm going to call the length of the adhesive bond L, lowercase l. So we have 2 pi R L for the surface area times tau. So that gives us V. And we get another R. So we can say that the T external, and I think we may be given that. Yeah, somebody tells it to us, and this is another test fixture, it looks like. So somebody applies 2 times 10 to the third Newton meters, and it breaks. And supposedly that's the lowest stress at which it broke. It held all the way up to there. So we can consider that was the breaking torque for this adhesive. So we've characterized something about the adhesive, which is pretty cool. But we don't characterize adhesives in terms of torque because it's got all of these characteristics of the test fixture. It's tau. It's the shear stress that we're going to relate to something on the adhesive and go, oh, that had a great shear stress. Let's buy more of that. Or, oh, that was too low for our application. Get a stronger one. Or if you're a material scientist, you might say let it cure a little longer and get a higher crosslink density. But regardless, we gotta use this expression to basically take away the effect of the test fixture. So we just do that with some algebra. So we say 2 times 10, this is 10 to the third, not minus third, Newton meters is going to equal tau, the quantity we want, times R times the surface area, so that ends up giving us R squared, times 2 pi times the length, the axial length in the z direction of the adhesive bond. So we're going to end up with tau being 2 times 10 to the third Newton meters divided by R squared times L times 2 pi. And so L is going to cancel the meters, and then we're going to have newtons per meter squared, which is the correct units for any kind of stress, including shear stress. And so this would be tau adhesive. So that would give us a measure of the shear stress of the adhesive itself. So if you wanted to be able to apply more torque, we can think of things, the relationship. Say we were stuck with this value. Oh, we only got this adhesive on the shelf. We got cyanoacrylate super glue. And well, doggone, I need to double that torque. What am I going to do? We could increase L by double. We could take that out to we could apply that adhesive over twice the length. If the pipes are the same radius, there's not much we can do there. But basically, you can see that the torque and the one dimension of that surface area over which the shear is applied, those are in a 1-to-1 ratio. So if we had the same radius, all we'd have to do was smear the glue over twice the area, and all other things being equal, we could double the applied torque for the same adhesive. Okay, so that's That's shear. Now we've covered shear in the two different orthogonal directions we have available on that R face, RZ, when we pull the cylinders apart, and then R theta when we, oops, my pointer here. This is not letting me point. Sorry about that. We're going to consider one more case here. Let's get our whiteboard pen ready to go here. So this is the next problem down, and it's very, very similar. And except instead of an adhesive, we've got a bolt. So somebody said, well, I don't have any glue, maybe, but I could just drill a hole, and we'll assume it's a small hole. Get our tablet going here. So let's consider the same case, except in this time somebody has, doesn't really matter, you know, the length over which they're joined now. But somebody has said, okay, I don't have any glue, I'm going to pin them together. So here's our center line. So this is again a longitudinal section through the concentric pipes. So they're contacting, so I sectioned them right down through that center line parallel to the z-axis. So this is Z. So this is this section. So somebody has, I'm going to draw it in orange, but it's not an adhesive, it's a through hole. So I got a through hole here. And somebody put a bolt. It's pinning together, and then went ahead and applied a torque. And it's the same one. I think it's also that 2 kilonewtons. Okay, so we have T applied equals 2 times 10 to the third Newton meters. Sorry, we applied Newton meters of torque. Okay, so we could give the same kind of argument that there's going to be a resultant shear in the R theta direction, shear force operating at this interface at big R, because the shear force is operating at the same, you know, if we look, it's obviously going to be resisted by this bolt here, through bolt in orange. And the point in that bolt at which the shear force is being applied, it's literally being applied through basically kind of, you can think of it through two planes here. These two planes are where the shear force is being applied across there. So V and V. So that's basically kind of an R direction from the standpoint of the bolt, and an R theta from the standpoint of the cylinders. But we're told, okay, you've applied the same as you did with this adhesive, and we're given a diameter on this bolt. I think it's 15 millimeters, so we can call it 15 times 10 to the minus 3 meters diameter. So, you know, R would be 7.5 times 10 to the minus 3 meters for the bolt, and it's at 50 times 10 to the minus 3 meters radius from our axis. So R cross V is going to give us, of course, our moment in the Z direction. I'll draw a little moment arrow there. So this time this time we don't have nearly as much area to carry that shear. We just have these little cross sections of this bolt carrying the whole thing, because our R cross V still has to equal T applied in both cases. So we have these double areas carrying it, but basically we know that R cross V, we basically have a couple moment that we have to carry all of our force. So it's going to end up being 2 times R cross V, and then 1 R cross V here, 1 R cross V here. So we'll have our basically a couple moment that's going to be opposing T applied. So a little bit of statics there. So our T applied is going to have to equal 2 times, I'm going to just write out the R cross V. These are perpendicular, so we're going to have 2 times R, which is 50 times 10 to the minus 3 meters, times V, which is going to be tau bolt, times surface area bolt cross section, XT's cross section. And so that's going to be a lot less. That's going to be pi times, this time we're going to square it, pi times 7.5 times 10 to the minus 3 meters squared. So give around and about 7 squared is 49, 7.5. So we'll call that times 3. So that's around and about 150 times. We're doing some real swag estimation. Order of magnitude approximately. Order of magnitude approximation. And so we have 50 times 10 to the minus 3. So we'll have 2 times 50, so we'll have 100 times 10 to the minus 3 meters times 150 times 10 to the minus 6 meters squared times tau bolt. I'm getting a little sloppy here. So this would be about 1 times 10 to the minus 1 2, 1.5 times 10 to the minus 4 will give us meters cubed. We had 2 times 10 to the third Newton meters. On the other side of the equation, we have our tau bolt, and I won't go any further with that, but you can get an idea. We're going to end up having something around 1 times 10 to the minus 5, and this is 10 to the third. So we're going to have quite a hefty shear stress. So we'll end up with something around in between 1 and 2 times 10 to the 8th. So that's between what, 10 and 200 megapascals, which is a reasonable shear stress, and that would be definitely something that might be challenging the yield, the shear yield of a lot of materials. So we would probably have to go to something with a fairly high yield, something like maybe a heat-treated steel or whatnot. And you can do some math and compare that to the average, and of course this is average. This is assuming that this entire cross-section area carries the same. Chances are that won't be true. We might have a little more on the front end than the back, but again, assuming it's an average shear, we can look at tau bolt as tau average over this whole cross-sectional face. But compare that over here, run the numbers and compare that to the average shear stress in the adhesive. You'll very likely find that the adhesive shear stress is much less. It is a polymer typically, after all, so it's not going to be expected to necessarily have the same capabilities. But one reason that you can get away, now I haven't run the numbers here on this particular problem obviously, so you'll have to compare them. But remember that in the case of that adhesive, and I'll blow it up again over here, we're applying that over a much bigger area. And so that's one of, when you think about ways, and you think about shear, and you think about ways to put things together, and the shear stress that you need to carry a given load, whether it's that normal force P or this torque T that we're applying, something to consider is how much area you want to use to spread that shear stress out over. In the case of our bolt, the configuration is requiring us to engage just the cross-sectional area of the bolt in a couple of places. We could maybe put a few more bolts in, and so we'd be engaging more cross-sectional areas. So the shear stress in each bolt would be engaging less, and as we put more and more bolts, eventually we would approach what we have over here with the adhesive, where we're using the whole area. So the more area that you can spread a load out over, the lower the stress, especially in shear, where you have quite a bit of overlapping area available. Unless you have to lightweight it, that's a design option that you might have in mind. So for instance, you were given some kind of project where you had to put two materials together to carry a certain load. You might consider what kind of thickness you needed on those round pipes, if you were looking at some pipes, and how much radius you could use for the interface, and then your material capabilities for your adhesive and for your pipes, and then how much insertion depth that you could allow for. The more insertion depth, the heavier the part, because it's doubled up over a larger area. It's going to be probably stiffer against buckling, which is another topic we'll look at later towards the end of the course. But you can get a huge area to spread that that load, that V over, that VR theta or that VRZ over, and wow, you have a lot more choices of things you can use, and none of them are going to be subject to stress risers. Again, another glimpse into the future. But the hole that we use to put that bolt through is going to, it's a local discontinuity in the stress field, and so that could cause some problems for the pipe materials. The adhesive wouldn't have that problem. So again, subject for later, but for now, V operating over an area, giving us a tau on the R face going in either direction, and then that backing out into equating to an applied normal load, P, N, which is usually N, or to a torque. And we got a simple case in that all of that V is operating at the same radius. So from the point of view of the torque, it's a simple VR. And that is it for our tale of well, I guess it was 2 loading, not 3 loading cases. But now hopefully you have a little bit better intuitive grasp on shear loading and shear stress.